Ever wondered why the sky appears blue or why clouds are white? It all boils down to a fascinating natural phenomenon known as scattering. At the heart of these everyday marvels is scattering, a process where light or other forms of radiation spread out in different directions as they encounter particles in their path. It's like a cosmic dance where light particles or photons pirouette and twirl, bouncing off atoms and molecules. And it's not just an abstract concept that scientists ponder over. It's a part of our daily life, affecting everything from the color of the sky to the visibility in foggy conditions. But here's the twist: scattering isn't a one-size-fits-all process. Just as there are many types of dancers, there are different types of scattering. Each type has its unique characteristics and influences how we perceive our world in subtle yet profound ways. Scattering is not just a single process but a collection of different types, each with its unique characteristics and effects. First on our list is Rayleigh scattering, named after the British scientist Lord Rayleigh. This fascinating phenomenon has everything to do with why our sky appears blue. But how does it work? Well, let's dive in. Rayleigh scattering occurs when light or other electromagnetic radiation interacts with particles much smaller than the wavelength of the light. The scattering is inversely proportional to the fourth power of the wavelength, meaning it's more effective at short wavelengths, those towards the blue end of the spectrum. So, when sunlight, a mix of many colors, infiltrates our atmosphere, blue light is scattered in all directions more than other colors because it travels in smaller, shorter blue waves. This scattered blue light is what we see when we look up. So the next time you marvel at the blue sky, remember, it's all thanks to Lord Rayleigh's discovery. Moving on, we have Mie scattering, another fascinating type of scattering. Unlike Rayleigh scattering, Mie scattering is not as partial to shorter wavelengths. This means it doesn't favor blue light over red, or any color for that matter. It treats all wavelengths of light equally, hence its label as wavelength independent. This type of scattering comes into play when light interacts with particles that are about the same size as the light's wavelength. Think about dust or water droplets. These particles scatter light in a way that doesn't favor any particular color, resulting in a white or gray appearance. You see Mie scattering at work every time you look up at a cloud. Those fluffy white formations? That's Mie scattering in action. The water droplets in the clouds are comparable in size to the wavelength of light, causing an equal scattering of all colors. Mie scattering, with its wavelength-independent nature, plays a significant role in the color palette of our environment. Lastly, we have non-selective scattering, a type that doesn't discriminate. In this intriguing process, light interacts with particles that are much larger than its wavelength. Unlike its counterparts, Rayleigh and Mie scattering, non-selective scattering doesn't play favorites with colors. All wavelengths of light are scattered equally, which is why it's called non-selective. This non-discriminatory scattering is what makes large clouds and fog appear gray or white to our eyes. When light encounters these large particles, it scatters in every direction, retaining the color of the original light source, usually white sunlight. This is why, even on a sunny day, a thick cloud can look a bit gray. It's all the colors of light being scattered equally and coming together. So, in essence, every time you gaze at a cloud-filled sky or find yourself enveloped in a dense fog, you're witnessing non-selective scattering in action. Whether it's the blue of the sky or the white of the clouds, scattering shapes our world in beautiful ways. So the next time you look up, remember, there's more to it than meets the eye.